Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T with another tutorial, and today we're ending our unit on functions by looking at real-world data and modeling them with functions. We'll talk about what modeling means. So when we're modeling something mathematically, we're trying to fit or create a function, an equation, that would predict that set of data or fit it. Fitting means if we sketch a graph of the data with a scatter plot and then we sketch the function, that the function would be closely aligned with the dots of data. The purpose of trying to take a set of data, say tabular form, and creating a function that models it is once we have the function, we can use our understanding of various function families to understand the behavior of that model. What happens at the end behavior, where there might be relative maximum minimums, etc. We can also, once we have a formula, we can use that function to predict other values for the experiment. So we can pick points where we didn't collect data, or we can try to extend or extrapolate the data to future values and use the function to make the predictions. In order to do modeling, we have to analyze the data that we're given. And first, before we try to fit a particular function, we want to understand what parent or function family best represents the data. If all the data is in a straight line, we could use a linear function. If the data, when looked at in a scatter plot, makes a U shape, we might use quadratic, or one of the other families. We'll be looking at that next. Once we have determined the function family, we will fit an equation using that family that best fits the data. And that process is called regression, and we'll talk about how we're going to do that. In this lesson, we'll be doing the creation of the functions using the graphing calculator. Some of the function families that we've worked with in Algebra 2 are listed here. Linear functions, which are straight lines; quadratic functions, which are U-shaped; exponential, this is exponential growth, but we could also do exponential decay; and the square root function. Now, one of the ways we can determine what function family for if we have tabular data is to look at finite differences or ratios between adjacent items in the data. Now, this process of using differences and ratios only works when the data is evenly spaced. So the x values have to be going evenly spaced, like every x value, 1, 2, 3, 4, 5, are going by fives, 1, 6, 11. They have to be evenly spaced out. For the square root function, since that is the inverse function of the quadratic, the x and y's are changed. So when we look at a square root function, we need the y values to be evenly spaced. It'd be a process of elimination, so the easiest thing to do is to subtract or find the difference between adjacent y values in the table. And if we do that for the entire table and we get a constant value, either the exact same value or values very close, then the function's linear. If that doesn't match, we may look at second differences, which means taking the differences of the first differences. So we subtract a second time. If those are constant, we have quadratic. If neither of the first or second differences are constant, then we might look at ratios of the y values in adjacent spots in the table. If those ratios are constant, then we have an exponential function. Finally, for the square root function, we actually take differences of the x values. Over here, we subtracted the y values and look for a constant second difference, which would be square root. So we'll apply these rules in the upcoming example. So here we have some data. We had a length of string, we get a spring, and the spring stretches depending on the weight that's attached to it. And so we did an experiment where we had a particular spring and we put different masses of weights on this spring and measured its length. And this would be a prime example where we want to model this with a function so that if we wanted to predict how long the spring would stretch, if we put on, say, a 20-pound weight, we could use the function. So the first thing to do is, now we are evenly spaced on the x's, so the first thing we might want to look at are the first differences. So we're going to take 32 minus 30.6, 33 minus 32, 34.8 minus that. We're going to do those subtractions. And in each case, we get the exact same number, 1.4. So these are called first differences. They are our first subtractions. And based on what we said here, if the first differences are constant, we have a linear function. So if we were trying to write a model, we would write a linear equation that goes through this data. We'll actually generate the models later in this unit. For now, we're just trying to determine what function family this data is associated with. In this example, we have some liquid, and it's, say, in an open container, it's an evaporating, and we're looking at how much liquid is left over time, and this time was measured in hours. Again, our data is equally spaced because we measured the data every hour. So now we can look at the first differences. We can subtract here, subtract here. Now the numbers are getting smaller, so the differences will be negative, and we get these first differences. So that's not constant. They're not the same, and they're not anywhere near the same. So the next step is look at the second differences. So we subtract those two numbers, subtract those two, subtract those two, subtract those two. These are called, when we subtract the second time, those are called second differences. If these were constant, meaning close to the same number, we would have a quadratic relationship. But these are not the same. So we know by looking at these that is not linear. And we know by looking at the second differences, it's not quadratic. So the next thing to look at are ratios. So we're going to take this number divided by that number, this number divided by the previous number. So we always take the furthest number divided by the previous number. All those ratios are here, and we get the exact same number each time. So this is an exponential function. And given that it's decreasing, we actually know that it's an exponential decay function. And again, we'll look at how to write the equation that models that data in a few seconds. Now, if the data is not evenly spaced, if we have like random times that we measure this data, then we can't use the difference in ratio technique, and we might want to look at a scatter plot of the data. We may want to look at graphically and look at, does the data seem to line up in a straight line? Does it line up in a U shape? Does it have this pattern, etc.? So the convenient way to do the scatter plots is with a graphing utility. So to make a scatter plot, we're going to enter the data into lists. Now we use this in our statistics unit. So remember, we turn our calculator on and we press the stat button, and the first item is edit, and we're going to put the data in the list. Now when we're using this for scatter plots, the list 1 will be the x points, the x values, and the L2 will be the y values. Or in terms of data collection, these are the independent data and the dependent data. So we'll enter all that data. To see the graph, once the data is in here, we have to program the calculator to do scatter plots. So we're going to press second y equals. So second y equals. And right now, these are we can have multiple plots, but we're going to use plot 1, and it's turned off. It's not displaying. So to turn it on, we're going to select item 1. And we have to do two things. We want to make sure that this says on, and this icon here is highlighted, which it already is, which would be the scatter plot. When we did box and whisker plots, we used this icon. So we're going to set this, so we have to turn this on, so we just press enter to toggle it to on. Another setup we have to do is possibly look at the window. When we look at window, these are the range of X values that will display on the screen and the Y. If our L1 column goes beyond either smaller than -10 or bigger than 10, we have to adjust those numbers. And if the output values, the Y values, the dependent values are outside that range, we have to change. Once we've set this up, then we'll press graph. So we're going to go through an example of this on the next slide. So here we have a set of data. Now this is equally spaced, and we can use the first and second differences to look at it. Now in this case, the first differences are not constant and the second differences are not constant. So then we could look at ratios. In this case, the ratios are relatively close. They're not exact. In the real world, data rarely perfectly fits these functions. It's usually, but these ratios are fairly close, so this data is exponential. Now this is what the scatter plot looks like if we did it by hand, but I want to review how to do this scatter plot using our graphing calculator. So remember, step one is to enter the data into our stat. Now, if you have data in these lists and you want to clear it, remember from our statistics unit, you press second and the plus key to get into the memory management menu, and we select item 4 to clear all lists and then press enter. That'll give you a nice clean list to start with. Now we have to enter these X values down the L1 column. And now we have to move over to the right to the L2 column and enter these numbers. So 124, 150, 185, 213, 261, and 322. Now we have our data. Now we have to think about the window. So our X values go from 5 to 10, and our Y values go up to 322. So we might want to set our window to, say, go from 0 to 10, and our Y values to go from, say, 0 to, say, 350. Now when we have big numbers here, we can use X scale. That'll adjust the tick marks. So here we might want to count by 50. So I'm going to set Y scale to 50. You don't have to change Y scale and X scale, but it makes the graph easier to read. So now we press graph and we see this. So that might be a exponential function. And since the first ratios were fairly close, exponential would be the correct model for that. Again, in a minute, we'll talk about how to generate that model. So again, that's scatter plot, generating scatter plots. Our last step is to generate an equation for our data. So all the work that we did to set the data up for scatter plots is going to be used. So we have to enter the data into L1 and L2. But now we're going to do, instead of graphing it, we're going to press the stat menu again, and we're going to go over to the calc menu, and we're going to do something called a regression. Regression means fitting data to points. Now we will pick the appropriate kind of regression depending on our function family. And the examples that we're using, we will be doing either linear regression, quadratic, exponential, or square root. For the data that's in my calculator, that was our last example, we determined that that was exponential. So I'm going to do exponential regression on this. So now that I have my calc menu, I'm going to scroll down to the 10th item, which is EXP regression, exponential regression. I'm going to press enter. Now, some calculators, you may have some other menus. What you're going to do is you're just going to press enter until you get a screen that looks like this. On some of the other calculators, you may have to press more than one. It gives you the template for our exponential model, y equals ab to the x, and then it tells you a and b. So if we go back to our previous example, the equation that fits this data is, we could use, say, b for the number of buffalo, equals a, which was, if we round that, say, to 48.58, times b, which is 1.207, raised to the x, or in this case, we'll use t for time. Now, if we wanted to see that overlaid with our data, we could go to y equals and enter that equation, 48.58 times 1.207 raised to the x power, and press graph. And we get our scatter plot, and then this is plotting our regression function. And we'll see here that it fits the data pretty good. It doesn't go through the middle of every point exactly, but it's pretty close. So if we were using this to predict how many buffalo we might have after, say, 20 hours, we could just plug 20 into t and make that calculation. So we have one more example here. So let's do a scatter plot. So let me clear out my lists, second plus 4, and I'm going to clear out this function I just entered in there. And we're going to enter the data, stat, edit, and I'm going to enter my x data here, 0, 10, 20, 30, 40, 50, 60. I'm going to go over to the L2 column, so I've got 300, 423, 596, 842, 1188, 1686, and 2354. Now my x values in my window have to go from, say, 0 to 60. Let me make it 70, so I've got to change x max to 70. And my y values go up to, say, 2500. And let me put this x scale back to 1 just to show you what happens if we don't play with the x scale. And the only thing that happens is we really can't read the tick marks. Now this, to me, looks like an exponential growth graph. So I'm going to assume it's exponential based on the scatter plot. And I'm going to do an exponential regression. So I'm going to go back to my stat menu, move over to calc, and I'm going to again go down and do an exponential regression. We've got lots of different types of regression we could do. And whoops, I hit enter too much. So my model here is y equals 299.9 times 1.035 to the x power. That's our model. And it's predicting the number of bacteria when we enter the minutes as the x value. So this says 3 hours, which is 180 minutes. So let's enter our equation and calculate. So this time we'll just type it in. So 299.9 times 1.035 raised to the 180 minutes. And then these are bacteria, so we'll round it to the nearest whole number. So we get 146,636. So 146,636 bacteria. Now we can use stuff from the last unit to answer C. We've got an exponential equation here. So tripling would be this. Remember, this is the initial amount, or in this case 300, so we could have rounded that. But we want to triple that. So we're going to have 900 equals, and let's just make this 300, because we knew our initial amount was 300. And we want to solve this for x. So remember, we've got to get from our unit on solving exponential equations, we want to get that by itself, so I have to divide by 300. So if I divide by 300, I get 3. And our method for solving exponential equations like this is to convert it to logarithm form. So we have log base 1.035, and the 3 and the x change places. And now we just have to remember how to calculate this. And remember, we use the change of base formula. So it's going to be the log of 3 divided by the log of our base, which is 1.035. And now I can just calculate that. So let's clear this off. So log of 3, close that parentheses, divide by log of 1.035, close that parentheses, press enter. And so x comes out to be 31.9, and we were measuring x in minutes. So 31.9 minutes, it would triple. Now that kind of makes sense because 300 was here, 900 would be between these two. And again, that would be somewhere between 30 and 40, which makes sense. So this number makes sense. So hopefully you've seen a bunch of good examples on how to do modeling of real-world data. This is one of the more practical and useful skills. Some of you, maybe you own a business and you're tracking your sales, maybe based the prices that you charge versus your sales, and you want a model to predict what's the best price to set for your units. Or maybe you're doing some other kind of business or scientific study where you're collecting data and you want to be able to do some more elaborate analysis. So good luck and see you around.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you